Hello everybody, thank you for joining me today. My name is Ian Renaud, and I'm going to be doing a short introduction on Maxwell's equations, what they are, and how they are used for. So, James Clerk Maxwell unified classical, electric, and magnetic equations. This provided our understanding of electromagnetism, as we know now, showed that light is an electromagnetic wave, and provided a basis for modern physics and relativity, the work that would come after his death. And here's a picture included of him. Alright, here are all of Maxwell's equations in both integral and differential form. The two forms represent similar ideas physically, and are just two ways mathematically to represent the terms. The first two are Gauss's laws for electricity and magnetism. The third is Faraday's law, which relates changing magnetic fields to electric fields. And finally is Ampere's law with Maxwell's modification, which considers systems with both changing fields and currents already enclosed. I will be going over each one of these and how they are used and how they relate to one another. First here is Gauss's law in integral form. This relates the electric field through a surface to an enclosed charge within that surface. When there is zero charge enclosed, the electric flux, or a measurement of how much electric field is going through a surface, is equaling to zero. A way this can be physically thought about is if you have a charge outside of a surface, an equal amount of flux would run in from one side and out of the other, totaling out to zero. And here's a short example on the right-hand side. To start, assume a constant charge Q is enclosed in a sphere. This generates a constant field E. So to begin, you can pull the electric field out of the integral, as it is a constant. This leaves us with the total enclosed surface area integral. And this can just be seen as the surface area of a sphere, which is equal to 4 pi r squared. And then you can plug this value back in, and this easily allows us to solve for E in terms of our constants, the charge, and radius. Now here is Gauss's law again in differential form. This equation shows the relation of how a field spreads over space. It's similar to the last one, except it doesn't need to be within an enclosed surface. The left-hand term represents the divergence of an electric field, or how much it is spreading out. The right-hand term is charge density divided by vacuum permeativity. This gives us the source strength of the electric field at some point, over a scaled potential. The integral and differential form can be related pretty easily through the divergence theorem, and as a reminder, I have the integral form from the previous slide here. The divergence theorem is an idea in math that lets us convert a surface integral to a volume integral. So the left-hand side is again the total amount of the electric field running through a surface, and this is equal to the total divergence of that electric field enclosed within that volume. We can plug this form back into this integral, pull out the vacuum permeativity constant, and this gives us the integral of charge density over a volume, which is the same as the charge enclosed. And this brings us back to our previous integral form from the last slide. So, moving on to the second equation, this is Gauss's law for magnetism. The left-hand equation is the differential one, and this states the divergence of B, where the magnetic field is always equal to zero, which means at all points the magnetic field has zero divergence. This shows magnetic field lines do not start or end, but rather like electric field lines, but rather loop around and start and end at the same point. So here at the bottom is a diagram included of an electric field, specifically a negative charge, and all the arrows point into it, meaning they do not start or end at the same point, whereas in a magnetic field, it has both a north and a south pole, and the arrows come out of the north and run into the south. And I am just now realizing some of these arrows are the wrong way. These are supposed to be the other way. But they start and end at the same point, so this would mean that their divergence in total is zero. Moving on to the integral form, the net magnetic flux through any closed surface is zero, which is a similar idea. So the magnetic field lines would enter the South Pole and exit the North Pole equally. So if you were to imagine a surface around this, the lines would be going in and out equally, again totaling to 0. And as far as we know, there's no magnetic monopole. The way this could be thought about is if you only had one half of this magnet, either the north or south end, and then it would behave more like how electric charges do. But as said, there's no known magnetic monopole. And again, these can be related pretty easily to one another through the divergence theorem, and a similar process is shown on the last slide. So this is the third equation, Faraday's law in integral form. And this is stating if a magnetic field through a loop is changing with time, then an electric field is induced. And the negative hand sign on the right hand side shows that this induced field is in the opposite direction of one another. So the left hand term represents the circulation of an electric field around an enclosed loop, and the right hand term represents the change in magnetic flux, or how much magnetic field is running through the surface over time. And here's another small example included on the right. So to start, assume a uniform magnetic field that is only time dependent, V of t, is ran across a perpendicular loop. So to start, you would take the time derivative of the magnetic flux to find the right hand side of the equation. So to find our magnetic flux, first it would just be, again, the magnetic field across the surface. And since in this case we're using a loop, this would be pi r squared. And next we take the time derivative of this. So this would just, again, you would keep our constants, pi r squared, and then the time derivative of the magnetic field, dV over dt. And then next we set this equal to our left-hand side of the equation, the circulation of the field. And again, this would just be E times 2 pi r, because in this case you're using the total distance around the loop, or the circumference. We cancel some of our like terms, and we're able to get our electric fields in terms of the radius and our rate of change r of our magnetic field. Continuing on, here's Faraday's law in differential form. And again, this shows a changing magnetic field results in a circulating E field. So the left-hand side is the curl of the electric field, or how much the field loops around some point. And again, the right-hand side is the rate of change of the magnetic field over a time dependence. And once again, this is negative to show that the induced field is opposite in magnitude to one another. So comparing to electrostatics, where the curl of the electric field always equals to 0, this is with stationary charge, therefore electric fields can only come from charges. And Faraday's law allows us a deeper understanding when using time-variant fields. So as in a magnetic field inside a loop changes, an electric field is induced around that loop. And generators use this process to drive current, for a physical example. Moving on to the final equation, this is the Ampere-Maxwell law. So the left-hand side is the integral form, and this shows us that the circulation of a magnetic field is caused by the total of, first, the conduction current through the loop, which is this term here, and the changing electrical flux through the bounded surface of that loop, which is the second term. And similarly, for the differential form, this shows us that the curl of the magnetic field has contribution from both the electrical current, which is the real current, you can think about it that way, being ran through, and then the changing electrical field, which is Maxwell's displacement current, the second term. And this equation can be used to derive the speed of waves and also the speed of light similarly. And finally, here's the derivation of finding the speed of the waves using Maxwell's equations. So to start, you would assume free space, so no charges or net currents in the system. And to begin, you would take the curl of Faraday's law, and we can use a vector identity to simplify the left-hand side when remembering Gauss's law in free space, del dot E equals 0. And this brings us down to this term here, negative del squared E equals the negative time derivative of the curl of B. And then from the previous slide, we can substitute the Maxwell-Ampere law into the right-hand side. So we put this into this term, and this results in negative mu naught epsilon naught times the second partial derivative of the electric field with time dependence. And again, we cancel the negative sign here, so we have del squared E equals to this term, and this form matches the standard wave equation, which I have right just here below it. And this allows us to we take this 1 over v squared and just set it equal to mu naught epsilon naught, which are the constants permeativity of free space and permeability of free space. And this allows us to solve for the velocity of electromagnetic waves, which we now know is the speed of light. And one's finally plugging in all these constants. And that brings me to the end. Thank you so much for joining me. I wish I could take questions, but I cannot in this format. And thank you for the EM semester. It was great.